On the 1st of July 2025, astronomers detected 3 IATLAS, the third confirmed interstellar object to enter our solar system after ʻOumuamua and Borisov. Unlike typical asteroids or comets, it comes from a distant star system, traveling at a velocity far beyond anything bound to the Sun. 3I Atlas offers a rare chance to study material from another part of the galaxy, but its speed and unknown trajectory also raise concerns about potential dangers. Its discovery reminds us of the universe's unpredictability, showing how fragile our planet is in the face of cosmic visitors and sparking urgent discussions about planetary defense and preparedness. Interstellar objects like 3 IATLAS are among the most enigmatic phenomena in modern astronomy. What makes them so puzzling is that, unlike the countless asteroids, comets, and minor planets that orbit the Sun in predictable paths, these objects are unbound. This means their trajectories do not circle around our star. They enter the solar system from elsewhere in the galaxy and continue on a hyperbolic path never to return. Observing such objects is incredibly rare. Before ʻOumuamua, in 2017, scientists had no confirmed detection of an interstellar visitor, and the subsequent discovery of comet Borisov in 2019 only deepened the intrigue. Each of these discoveries raises fundamental questions about the composition, origin, and behavior of matter outside our solar system. The very fact that 3 IATLAS is traveling at speeds well above the solar escape velocity signals that it did not originate here. It was ejected from another star system, likely by gravitational interactions with its parent star or giant planets. Unlike most objects that have formed within the relative stability of our solar system, interstellar objects carry with them the chaotic history of distant planetary systems, making them unpredictable and almost alien in every sense. The speed of these interstellar visitors is a key factor that makes them so confounding. 3I Atlas, like ʻOumuamua and Borisov, travels at tens of kilometers per second, far faster than typical solar system objects. For astronomers, this high velocity complicates detection, observation, and trajectory prediction. Most telescopes and survey programs are designed to track slower-moving bodies, such as near-Earth asteroids, which provide ample time for detailed observation. In contrast, a hypervelocity object like 3 IATLAS can appear, be tracked for a brief period, and then disappear beyond the reach of observation instruments within weeks or even days. This fleeting window makes it difficult to study composition, structure, and behavior. Furthermore, the high speed means that any small errors in measurement of position, velocity, or acceleration can drastically alter predicted trajectories, introducing enormous uncertainty into calculations about whether an object might pass harmlessly by, graze a planet, or, in worst-case scenarios, collide. Adding to the mystery is the question of their origins. While it is theorized that interstellar objects are likely ejected from the planetary systems of other stars, the details remain elusive. They could have been flung out during chaotic planetary migrations, stellar explosions, or interactions with other massive objects in their home systems. The fact that we have detected so few suggests that either such ejections are rare or that interstellar space is so vast that the chances of one passing near Earth are extremely low. Every new discovery therefore carries immense scientific significance. It is a direct sample of material from a completely different star system, potentially carrying isotopic compositions, mineralogical structures, and molecular compounds that have never been seen in our solar system. The implications are staggering, as these objects could help us understand the formation and evolution of other planetary systems, the prevalence of water or organic molecules in the galaxy, and even the likelihood of life beyond our Sun. Interstellar objects also challenge conventional astrophysics because they do not behave in entirely predictable ways. ʻOumuamua, for example, exhibited unusual acceleration that could not be fully explained by typical cometary outgassing, leading to wild speculation about its true nature, including possibilities ranging from a tumbling, elongated rock to an artificial probe. While 3I Atlas has not yet shown such anomalous behavior, its mere classification as an interstellar object forces scientists to confront the limits of current models. We cannot assume that materials from another stellar system will obey the same rules as those in our neighborhood. The differences in formation conditions, radiation exposure, and stellar interactions might produce objects that defy expectations in density, shape, spin, or composition. Moreover, interstellar objects underscore how little we know about the dynamic exchange of matter across the galaxy. While planets, asteroids, and comets are usually studied as isolated within their home systems, interstellar objects demonstrate that material can and does travel between stars. Every hypervelocity visitor is a piece of a cosmic puzzle, carrying clues about gravitational interactions, planetary migrations, and possibly even the early processes of planet and star formation. The fact that these objects remain invisible until they are detected near the inner solar system points to a vast population of wandering debris in the Milky Way, much of it likely traveling unnoticed in the darkness between stars. This invisible population may occasionally intersect with planets, posing both opportunities for study and potential risks. The rarity of interstellar visitors is precisely what makes 3I Atlas such a source of fascination and concern. Unlike ordinary asteroids that the planetary defense community has catalogued and continues to monitor, these visitors arrive without warning on trajectories that may intersect with Earth or other planets at extreme speeds. This unpredictability forces astronomers to rapidly mobilize observation networks, perform trajectory analysis, and consider potential scenarios, including worst-case impacts. In addition, because we know so little about their structure, composition, and behavior under high-velocity solar system interactions, any prediction carries inherent uncertainty. Will it break apart when subjected to solar radiation and tidal forces? Could it harbor volatile compounds that produce outgassing and change its path mid-flight? Or could it, in the most extreme and speculative scenarios, be more than a rock, hinting at technologies or phenomena beyond current human understanding? Each question amplifies both scientific intrigue and existential anxiety. 3I Atlas stands out from its interstellar predecessors in several remarkable ways, making it an object of intense study and speculation. Unlike ʻOumuamua, which was elongated and exhibited unusual non-gravitational acceleration that baffled astronomers, or Borisov, which behaved more like a conventional comet with a visible coma and tail, 3I Atlas presents a set of characteristics that are both familiar and puzzling, straddling the line between the known and the unknown. Its trajectory through the solar system is faster and steeper, meaning it is on a sharper hyperbolic path that suggests an even more violent ejection from its home system, possibly due to gravitational interactions with massive planets or a close stellar encounter. Its speed is notable not just in absolute terms, but because it exceeds what we observed in ʻOumuamua, implying it may have come from a region of the galaxy where stellar dynamics are more chaotic, or that it was accelerated by unknown mechanisms before arriving in our solar system. The sheer velocity alone alters the way it interacts with the Sun and planets, affecting potential fragmentation, heating, and radiation exposure in ways that are distinct from its predecessors. Compositionally, 3I Atlas also appears to be an outlier. ʻOumuamua showed little to no visible outgassing despite its close approach to the Sun, which led to speculations that it could be a rocky or metallic body rather than a comet, while Borisov behaved like a typical comet, releasing gas and dust as expected. Early spectral observations of 3I Atlas suggest a composition that does not neatly fit into either category. It may have a hybrid structure, partially icy and partially rocky, or contain exotic materials rarely seen in our solar system. This raises intriguing questions about the diversity of planetary systems elsewhere in the Milky Way, and the kinds of objects they can eject into interstellar space. Unlike the two previous visitors, which gave us limited glimpses of their structure, 3I may carry clues about processes and materials that have never been sampled before, essentially acting as a cosmic probe from a foreign planetary system, offering unprecedented insight into the variability and complexity of objects that drift between the stars. Another factor that sets 3I Atlas apart is its size and potential for interaction with planetary bodies. ʻOumuamua was relatively small, estimated at a few hundred meters in length, and Borisov was a comet of moderate size, with a nucleus possibly a kilometer or two across. Early observations suggest that 3I Atlas could be significantly larger, raising the stakes for both scientific observation and hypothetical impact scenarios. Its size, combined with its high velocity, gives it an energy potential that is orders of magnitude greater than either of its predecessors, making it not just an object of curiosity, but also one that could, in a worst-case scenario, pose a real threat to planets in its path. While scientists remain careful not to overstate the danger, the combination of size, speed, and unknown composition demands attention and detailed modeling to understand what might happen if it were to interact with planetary bodies, satellites, or even the Earth itself. Its trajectory and approach also present unique observational challenges. Whereas ʻOumuamua and Borisov were discovered with relatively limited warning, 3I Atlas was detected farther out in the solar system, providing slightly more time for astronomers to study its path, velocity, and physical properties. However, its high inclination and steep hyperbolic trajectory mean that even small observational errors can translate into large uncertainties in predicted positions, especially as it nears the inner solar system. This makes 3I Atlas not only a fascinating object scientifically, but also a reminder of how difficult it is to track and predict the behavior of interstellar visitors with precision. Its differences highlight the growing need for sophisticated observation networks and rapid response strategies capable of monitoring fast-moving, unpredictable objects, as each new interstellar visitor could bring both groundbreaking scientific insight and potential hazard. Perhaps most intriguingly, 3I reignites the debate about the diversity of interstellar objects. ʻOumuamua challenged scientists to rethink conventional classifications, leading to theories ranging from elongated asteroids to artificial objects, while Borisov appeared to fit more comfortably within existing comet models. 3I Atlas, with its unusual speed, size, trajectory, and composition, defies simple categorization, suggesting that the galaxy may be teeming with objects of forms and behaviors we have yet to encounter. This challenges astronomers to broaden their observational and theoretical frameworks and prepares the scientific community to confront surprises that go beyond the limits of current understanding. In this sense, 3I Atlas is not just different. It may be the most enigmatic interstellar visitor yet, bridging the gap between natural phenomena and the tantalizing possibility of encountering objects that test the very boundaries of astrophysics and planetary defense. 3I Atlas is currently moving on a highly hyperbolic trajectory that distinguishes it from the familiar orbits of planets, asteroids, and comets within our solar system. Its path indicates that it is traveling at a velocity exceeding the Sun's escape speed, meaning it is not gravitationally bound to the solar system and will eventually continue outward into interstellar space, never to return. The object approached from the outer regions of the solar system, entering the gravitational influence of the Sun from a direction far removed from the plane of the planets, which has made it particularly difficult to track during the initial observations. Unlike typical comets, which often approach along more predictable ecliptic paths, 3 IATLAS's steep inclination gives it a trajectory that crosses the orbits of multiple planets at varying angles, creating complex gravitational interactions that astronomers must account for when predicting its motion. Early calculations suggest that it will pass relatively close to the inner planets before moving back out toward the edges of the solar system, but the exact approach distances remain uncertain due to the high velocity and limited observation window. Its high speed, estimated at tens of kilometers per second, means that the time spent in the inner solar system will be short, but the implications of its trajectory are profound. As 3I Atlas moves inward, solar radiation and gravitational forces from planets like Jupiter, Saturn, and even Earth could slightly alter its path, creating small deviations that compound over distance. While current models show no immediate risk of collision with Earth, the very steep hyperbolic path and extreme velocity make the margin for error small. Any miscalculation in its position or velocity could drastically change predictions for its closest approach. In essence, the object is threading a narrow gravitational corridor through the solar system, influenced by the combined pull of the Sun and its planets, all while moving at a speed that allows little time for detailed observation or response. Astronomers are particularly focused on how 3 IATLAS will interact with Jupiter and other massive planets, because even slight gravitational nudges from these giants could alter the object's trajectory in ways that are magnified when it reaches the inner solar system. Jupiter, with its immense gravity, often acts as a cosmic gatekeeper, deflecting comets, asteroids, and debris from the outer solar system, or redirecting their paths. For an object traveling as fast and steeply as 3I Atlas, even minor deflections could slightly increase or decrease the object's perihelion distance, the closest point to the Sun, potentially moving it nearer to Earth's orbit than initially predicted. Conversely, gravitational interactions could also accelerate the object, decreasing the time it spends near the Sun and limiting opportunities for study. Each adjustment in its trajectory, however minor, must be calculated with extreme precision because the combination of high velocity and hyperbolic motion amplifies the impact of even the smallest observational uncertainties. Beyond gravitational influences, the trajectory is also shaped by non-gravitational effects, such as outgassing if the object contains volatile ices. Although early observations have not detected significant comet-like activity, the potential for sublimation when 3I Atlas approaches the Sun could alter its path. Outgassing produces small thrusts that act like invisible rockets, nudging the object unpredictably. Such forces were observed in ʻOumuamua, which demonstrated acceleration inconsistent with gravitational influences alone, sparking debates about whether it was purely natural or possibly artificial. While 3I Atlas has not shown such anomalies yet, astronomers remain vigilant, knowing that even subtle changes in trajectory could influence predictions for inner solar system encounters. This combination of hyperbolic velocity, gravitational perturbations, and potential outgassing makes modeling the trajectory exceptionally challenging and underscores the inherent uncertainty in forecasting the object's path. Current predictions place 3I Atlas on a course that will take it past the inner planets, with Earth remaining safely distant under the most probable scenarios. However, the exact distances are difficult to pin down. And as it moves closer, astronomers will continue refining calculations using data from powerful ground-based observatories and space telescopes. Tracking such a high-speed interstellar visitor requires constant observation, precise astrometric measurements, and sophisticated computational models that account for all known forces acting on the object. Its passage provides a rare and fleeting opportunity to gather information about a body from outside our solar system, while also highlighting the fine line between a safe flyby and a scenario where minor changes in trajectory could bring catastrophic consequences. Despite the best efforts of astronomers to calculate 3 IATLAS's trajectory, uncertainty remains a significant factor, and it is precisely this uncertainty that fuels both scientific fascination and public concern. Even the smallest errors in measuring the object's position, velocity, or acceleration can drastically alter predictions for where it might pass in the inner solar system. At tens of kilometers per second, 3I Atlas covers vast distances in extremely short time frames, meaning that even a miscalculation of a few meters per second in its velocity could translate into thousands of kilometers of positional error by the time it reaches the vicinity of Earth or other planets. These tiny observational discrepancies arise from limitations in our instruments, atmospheric distortions for ground-based telescopes, or incomplete data coverage during its initial detection. When tracking an object already traveling at interstellar speeds along a steep hyperbolic path, such small margins of error are amplified exponentially, creating a complex web of possible future positions that must be continually refined. The challenge is compounded by the fact that 3I Atlas is a hyperbolic object, not gravitationally bound to the Sun. This means that its path through the solar system is influenced not only by solar gravity, but also by the gravitational pull of planets, particularly massive ones like Jupiter and Saturn. These gravitational interactions can slightly deflect the object's trajectory, and if such perturbations occur in combination with minor measurement errors, the cumulative effect can produce a significant divergence from initially predicted paths. For example, a misestimation of a small acceleration due to outgassing, or even pressure from solar radiation, could mean the difference between a harmless flyby and a near-miss scenario, or in extreme hypotheticals, an impact trajectory with Earth. Unlike asteroids whose orbits have been stabilized over millions of years, interstellar objects arrive with no such predictable history, and every new piece of observational data can drastically shift the set of possible outcomes. Computational modeling of 3IATLAS illustrates the sensitivity of its path to minor changes in initial conditions. Using current data, astronomers can generate a range of possible trajectories, known as a confidence region, which represents all the positions the object could occupy given observational uncertainties. Early calculations show that while the most probable path keeps 3IATLAS well clear of Earth, the edges of this confidence region extend dangerously close to our planet and other inner solar system bodies. This inherent unpredictability is a reminder that high-speed interstellar objects operate on a razor-thin margin. The faster an object moves, the more even tiny discrepancies matter. As a result, ongoing observation campaigns are crucial to narrow down uncertainties and refine predictions. But even with state-of-the-art telescopes and computational power, some level of residual unpredictability remains. Another layer of complexity comes from the possibility that 3IATLAS may not be a monolithic object. If it contains internal fractures, heterogeneous materials, or volatile regions, it could experience uneven forces as it moves through varying gravitational and radiative environments. Even minuscule asymmetries in structure can produce slight rotational torques or thrust from sublimation, which over the short but rapid course through the inner solar system can alter its path significantly. This is a lesson learned from Oumuamua, whose anomalous acceleration could not be fully explained without considering subtle forces acting over long distances. If 3I Atlas behaves similarly, astronomers must contend not only with observational error, but also with natural, unpredictable dynamics intrinsic to the object itself. The consequences of these uncertainties are magnified when considering worst-case scenarios. While the most likely outcome is a safe passage through the solar system, the potential for an impact cannot be entirely ruled out until the object has passed its closest approach. Even a small chance, measured in fractions of a percent, represents a high-stakes scenario given the energy carried by an object of its estimated size and velocity. To put it in perspective, an object a few kilometers across traveling at tens of kilometers per second would release energy orders of magnitude greater than the most powerful nuclear weapons if it were to collide with Earth. This is why astronomers stress continuous monitoring, recalibration of trajectory models, and readiness for hypothetical mitigation despite the extremely low probability of direct collision. In the case of interstellar visitors, small observational errors are not merely academic. They are the difference between benign flybys and planetary-scale disasters. Furthermore, these uncertainties also affect predictions for planetary flybys, satellite encounters, and potential debris interactions. A tiny deviation in trajectory could result in 3 IATLAS passing closer to a planet like Mars or Venus than expected, or even intersecting with artificial satellites and space infrastructure in orbit. This cascading effect shows that uncertainty is not limited to predicting a single impact point. It influences a network of possibilities that can ripple across the solar system. Each new observation reduces uncertainty, but can also reveal unexpected behaviors, highlighting the dynamic, ever-changing nature of predicting the paths of hypervelocity interstellar objects. In essence, 3I Atlas exemplifies the fragile balance between precise astronomical modeling and the uncontrollable reality of high-speed objects from beyond our solar system, reminding humanity that even a tiny measurement error can scale into consequences of planetary significance. In the extremely unlikely but theoretically possible scenario that 3 IATLAS were on a direct collision course with Earth, the consequences would be catastrophic, and the scale of devastation would depend heavily on its size, composition, and speed. Even a relatively modest object, a few hundred meters across, would release energy equivalent to millions of tons of TNT upon impact, generating a fireball, shockwaves, and regional destruction over thousands of square kilometers. The immediate area surrounding the impact site would be obliterated, cities reduced to rubble, and infrastructure vaporized. Thermal radiation from the impact would ignite fires for hundreds of kilometers, creating firestorms that could devastate ecosystems and human populations far from the initial strike. The atmosphere would carry immense amounts of dust, debris, and aerosols into the stratosphere, blocking sunlight and triggering a temporary but intense cooling effect, an immediate precursor to a localized impact winter. If 3I Atlas were larger, spanning several kilometers, the scenario escalates dramatically. The energy released would dwarf any modern weapon, equivalent to billions of tons of TNT, and could rival the global effects of past mass extinction events. The impact would generate massive seismic activity, potentially triggering earthquakes and volcanic eruptions across fault lines thousands of kilometers away from the impact site. The immediate blast radius could extend hundreds of kilometers, flattening everything in its path, while ejecta thrown into the upper atmosphere would spread globally, causing darkness and plummeting temperatures for months or even years. Ocean impacts would produce enormous tsunamis, wiping out coastal cities and altering marine ecosystems permanently. Agriculture would collapse as sunlight diminishes, triggering famine and global food shortages, while fires on land would inject additional carbon and soot into the atmosphere, compounding climatic disruption. Humanity would face a combined environmental and societal catastrophe of unprecedented scale, with survival dependent on geographic luck and disaster preparedness on a global scale. The composition of 3 IATLAS would also dramatically influence the outcome. If it were a dense metallic or rocky object, the penetration of the crust would be extreme, delivering its full kinetic energy into the mantle and amplifying seismic and thermal effects. A less dense, icy or porous object might disintegrate partially in the atmosphere, creating a series of airbursts rather than a single surface impact. Even in this scenario, the energy released could level cities, destroy infrastructure, and create multiple large craters, as seen in historical meteor airbursts like Tunguska in 1908, but on a much larger scale, given the speed and mass of an interstellar object. Multiple airbursts could produce a cascade of secondary effects, sending shockwaves and thermal radiation across vast regions, igniting widespread fires and raining down debris over hundreds of kilometers. Beyond the immediate terrestrial consequences, a direct collision of 3 IATLAS with Earth would trigger global environmental and ecological repercussions. Dust and debris injected into the stratosphere would reduce sunlight, cooling the planet and disrupting photosynthesis, leading to food chain collapse on land and in the oceans. Acid rain from vaporized materials could further damage ecosystems and human settlements. In extreme scenarios involving larger impactors, the global climate could resemble the nuclear winter models, with prolonged darkness, freezing temperatures, and the collapse of agriculture worldwide. Wildlife, already stressed by habitat loss and climate change, would be decimated, while human populations could be forced into mass migrations, societal breakdown, and potential conflict over dwindling resources. The combination of physical destruction, climatic upheaval, and societal stress would make recovery extraordinarily difficult, potentially resetting civilization in the most extreme cases. Considering that 3I Atlas is an interstellar object traveling at speeds far higher than typical solar system bodies, the energy released in a collision would be magnified by its extraordinary velocity. The kinetic energy of an impact is proportional to the square of velocity, meaning that even a small increase in speed results in a dramatic escalation of destructive potential. This makes 3I Atlas a far more dangerous hypothetical threat than an ordinary asteroid of similar size. In addition, its hyperbolic approach limits the time available for mitigation, as it would arrive at Earth with little warning relative to slower, predictable near-Earth objects. Conventional planetary defense strategies, such as deflection missions or nuclear disruption, might be ineffective due to the short reaction time and immense energy required to alter its trajectory, emphasizing the vulnerability of our civilization to rare but high-impact cosmic events. In summary, while the probability of a direct collision is extraordinarily low, the potential consequences cannot be understated. From city-level destruction for smaller objects to global environmental catastrophe for multi-kilometer bodies, 3I Atlas exemplifies the ultimate high-stakes scenario in planetary defense. Its combination of speed, potential size, and interstellar origin makes it a uniquely dangerous visitor, illustrating just how fragile human civilization is in the face of cosmic hazards. Even with low odds, modeling these scenarios is crucial for understanding the range of possible outcomes and preparing for the extraordinary, reinforcing the reality that a single object from beyond the stars could, in theory, change the course of life on Earth forever. If 3I Atlas were to strike Earth in the worst-case scenario, the consequences would unfold in a sequence of planetary-scale disasters, each compounding the next, creating a global impact event unlike anything in recorded human history. Upon collision, the kinetic energy released would vaporize the impact site almost instantly, sending massive amounts of rock, soil, and atmospheric gases hurtling into the air at tremendous speeds. The immediate area, spanning tens to hundreds of kilometers depending on the object's size, would be obliterated. Cities, forests, and infrastructure would vanish in seconds under the shockwave and intense heat, igniting firestorms that could consume entire regions. The thermal radiation would not be confined to the impact zone. It would radiate outward, igniting fires in distant areas and creating a belt of destruction that could extend for thousands of kilometers from the epicenter. The combination of immediate impact devastation and widespread firestorms would create an environment inhospitable to human and animal life alike, forcing the collapse of local societies even before global effects take hold. Simultaneously, the impact would generate colossal tsunamis if it occurred in an oceanic region, with waves reaching hundreds of meters in height near the impact site and still tens of meters high, thousands of kilometers away. Coastal cities across multiple continents would be inundated, drowning populations, displacing millions, and destroying critical infrastructure such as ports, power plants, and transportation networks. Inland areas would not be spared either, as rivers and lakes could overflow due to the massive redistribution of water, further spreading destruction. The combination of firestorms on land and mega tsunamis at sea would create a chaotic, rapidly deteriorating environment, making immediate human survival a matter of both luck and preparedness. Emergency services would be overwhelmed and global communications disrupted, leaving humanity largely blind to the scale of devastation unfolding across the planet. The impact would also inject enormous quantities of dust, aerosols, and vaporized rock into the stratosphere, effectively blocking sunlight for months or even years. This phenomenon, often referred to as an impact winter, would drastically lower global temperatures and disrupt climate patterns. Crops would fail, ecosystems would collapse, and famine could become widespread, affecting regions far removed from the impact site. Acid rain, generated from atmospheric chemical reactions, would damage soil and water systems, poisoning crops and freshwater supplies. Even regions untouched by firestorms or tsunamis would face the long-term consequences of prolonged darkness, plummeting temperatures, and chemical contamination. The combination of sudden, violent destruction and a lingering environmental catastrophe would challenge humanity's ability to recover, potentially pushing societies into a prolonged period of struggle or collapse. Mass extinctions would be a likely outcome if the impact were of sufficient magnitude. Entire species of animals, plants, and microorganisms could vanish in weeks or months, unable to adapt to the rapidly changing conditions. Ocean ecosystems, in particular, would be severely disrupted as sunlight penetration drops, affecting phytoplankton populations, the base of the marine food chain, and cascading up to larger species, including fish and marine mammals. Terrestrial ecosystems would suffer from loss of vegetation, fires, and the sudden climate shift, forcing migrations and creating competition for dwindling resources. Extinction-level events are rare, but the potential of a hypervelocity interstellar object, like 3I Atlas striking Earth, is precisely the kind of scenario that could replicate the conditions of past mass extinction events, such as the one that wiped out the dinosaurs 66 million years ago. Beyond ecological and climatic effects, human civilization itself would face an existential threat. The destruction of major urban centers, collapse of agriculture, contamination of freshwater supplies, and interruption of global trade would challenge governance, social cohesion, and survival. The global economy, already highly interconnected, would falter under the combined strain of infrastructure loss, trade disruption, and workforce decimation. Medical care, sanitation, and energy supply networks could collapse, amplifying mortality beyond the immediate impact and secondary environmental effects. The chain reaction of disasters highlights how a single interstellar collision could ripple through every aspect of human society, turning what might initially seem like a regional catastrophe into a truly global crisis. Even the psychological impact would be immense. The sudden realization that Earth is vulnerable to interstellar visitors capable of erasing civilizations would alter human perception of safety, security, and our place in the universe. Societies could face widespread panic, social unrest, and breakdown of normal order as the enormity of the event sinks in. Communities might struggle to organize response efforts amid the chaos, particularly with the loss of communication networks and central governance. Historical examples of disasters suggest that human response often compounds the initial problem, and in the case of a global impact event, this effect would be magnified on an unprecedented scale. The cumulative picture of a global impact event caused by 3 IATLAS is staggering. Firestorms flattening cities, tsunamis wiping out coastlines, dust and debris plunging the world into an extended winter, mass extinctions reshaping ecosystems, and human civilization teetering on the brink of collapse. All stem from the simple fact that the kinetic energy of a hypervelocity object is unimaginably large compared to conventional disasters. While probability may remain low, the potential consequences highlight the thin line between the stability of modern life and catastrophic vulnerability. The event underscores the importance of continued astronomical observation, planetary defense research, and international coordination to monitor and, if possible, mitigate threats from objects traveling from the depths of interstellar space. If 3I Atlas were to strike the Moon instead of Earth, the consequences would still be catastrophic, though the effects would be indirect rather than a direct global annihilation. The Moon, though smaller than Earth, plays a critical role in stabilizing our planet's axial tilt, regulating tides, and influencing long-term climate patterns. A high-velocity impact by an interstellar object could eject massive amounts of lunar material into space, ranging from fine dust to enormous boulders, some of which could enter Earth's gravitational influence. Depending on the size and speed of 3 IATLAS, the collision could blast enough debris into orbit to create a temporary but extremely hazardous debris field around Earth, endangering satellites, space stations, and even crewed missions. Such an event could trigger a domino effect in orbit, where collisions between debris fragments produce more debris in a cascading chain reaction, known in orbital mechanics as the Kessler syndrome, potentially rendering low Earth orbit unusable for years or decades. Communication, navigation, and weather satellites could be severely disrupted, leaving humanity blind to both terrestrial and cosmic events. The Moon itself might also experience a measurable shift in orbit from a sufficiently energetic impact. While the Moon is massive relative to the scale of human-engineered satellites, the injection of extreme energy from a hypervelocity interstellar collision could alter its trajectory slightly. Even small changes in the Moon's orbit or rotation could have significant long-term consequences on Earth. Tides, for example, rely on the Moon's stable orbit. Changes could disrupt coastal ecosystems, marine life cycles, and even weather patterns that depend on ocean currents. Over time, these orbital disturbances could destabilize the delicate balance of Earth-Moon gravitational interactions, creating subtle but wide-reaching effects that ripple through our planet's environment. Debris raining down on Earth would be another major consequence. While most of the material would burn up during atmospheric entry, larger fragments could survive and strike the surface, creating localized but highly destructive impacts. Depending on the quantity and size of these fragments, regions across the globe could face city-level destruction without warning. The combination of multiple impacts could produce firestorms, shock waves, and localized climate effects, similar in scale to small asteroid strikes but occurring in clusters. Even if no single fragment reaches the size of a catastrophic asteroid, the cumulative effect of hundreds or thousands of impacts could cause widespread chaos, particularly in densely populated areas. Agriculture and infrastructure would be affected, and emergency response systems could be overwhelmed by simultaneous incidents in different locations. Furthermore, dust and ejecta from a moon impact could enter the upper atmosphere, temporarily dimming sunlight and affecting global temperatures. Although not as severe as a direct Earth impact, this lunar winter effect could disrupt crop production, reduce photosynthesis, and trigger minor to moderate climate anomalies worldwide. The Moon's material, unlike Earth-based impacts, would not include volatile organic compounds or water vapor, but the sheer volume of dust and aerosols would still have measurable effects on solar radiation reaching Earth's surface. In addition, the aesthetic impact of such an event would be profound. Massive plumes visible from Earth, craters forming on the lunar surface, and debris streaking across the night sky would serve as a constant reminder of humanity's vulnerability to cosmic hazards. An impact on the Moon would also have psychological and societal consequences. Seeing the Moon scarred or partially disrupted would be unprecedented in recorded history, challenging human perceptions of the stability of our celestial neighborhood. In the grand scheme, a collision with the Moon would not instantly annihilate life on Earth, but it would introduce a cascade of cascading problems. Debris hazards in orbit, potential shifts in the lunar orbit affecting tides and climate, fragmentary impacts across the planet, and disruption of human infrastructure and perception of safety. It demonstrates that even when Earth is not the direct target, the consequences of an interstellar object can still reverberate through the solar system, affecting our planet indirectly in ways that could challenge human civilization for years or decades. The Moon's role as a stabilizing force highlights the interconnectedness of celestial mechanics and life on Earth. Damaging it could set off effects that are both immediate and insidious, reminding us that cosmic threats do not need to strike directly to be catastrophic. If 3I Atlas were to collide with Mars, the consequences would be both immediate and far-reaching, though largely confined to the red planet rather than directly threatening Earth. Mars has become the focus of intense exploration efforts, with multiple rovers, landers, and orbiters studying its surface, atmosphere, and potential habitability. A direct impact by a hypervelocity interstellar object would obliterate any surface installations within the strike zone and could potentially destroy orbiting satellites if ejected debris or shockwaves reach space. Scientific equipment, long-term research projects, and invaluable data could be lost instantly. In addition, the collision would scatter regolith, dust, and debris across vast areas, potentially altering terrain features for hundreds or thousands of kilometers and complicating future landings, exploration, and research missions. A crater the size of a small city, or larger, depending on 3I-ATLAS's dimensions, could permanently modify Mars's surface, erasing geological features of interest and disrupting ongoing studies of its composition and history. For humanity's long-term ambitions on Mars, including colonization and the establishment of permanent bases, such an impact would be a severe setback. Proposed habitats and infrastructure, ranging from inflatable modules to advanced energy systems, would be extremely vulnerable to shockwaves and debris ejected by the impact. Even if structures were built far from the impact site, atmospheric dust could blanket regions of Mars, reducing sunlight, interfering with solar power generation, and contaminating sensitive equipment. Landing sites planned for human missions could be rendered unsafe or unusable due to the sudden redistribution of surface materials or the creation of unstable terrain. Water ice deposits, critical for sustaining human life and fuel production, could be buried, vaporized, or scattered, complicating resource extraction for decades. Essentially, the Martian environment would become far more hostile and unpredictable, delaying or potentially halting colonization plans until detailed reconnaissance and remediation could be carried out. From an exploratory perspective, a large impact by 3 IATLAS would also create a temporary scientific windfall in the form of exposed subsurface materials. The collision could excavate ancient rock and ice layers that have been hidden for billions of years, providing a rare glimpse into Mars's history, composition, and perhaps even its past potential for life. However, accessing these materials safely would be challenging, as the immediate vicinity would be unstable, potentially riddled with freshly formed craters and unstable regolith. Robotic missions would need to navigate a dangerous and rapidly changing environment, making the post-impact period one of both risk and opportunity. The challenge would lie in balancing the scientific value of newly exposed Martian strata against the hazards of operating on a planet that has been violently reshaped. Psychologically, an interstellar impact on Mars would alter perceptions of the viability of human expansion into space. Humanity has been gradually preparing for the eventual colonization of the Red Planet, seeing it as a potential second home in case Earth becomes threatened. An impact by 3I Atlas would highlight the vulnerability of even distant planets to cosmic hazards, reminding us that no location is entirely safe from celestial threats. This realization could spur a re-evaluation of space infrastructure design, planetary defense strategies, and investment in resilient habitats capable of surviving both human-made and natural cosmic challenges. International collaboration might be emphasized more strongly, as a single planetary disaster demonstrates that interplanetary risks are global in nature. Overall, while an impact on Mars would not directly threaten Earth, it would dramatically disrupt exploration and colonization efforts. Surface installations would be destroyed, orbital satellites endangered, landing sites rendered unsafe, and critical resources displaced. The long-term timeline for establishing a permanent human presence on Mars would be extended, and the perception of space as a frontier for human survival would shift to include a heightened awareness of unpredictable interstellar hazards. In essence, the collision would serve as both a cautionary tale and a practical challenge, demonstrating that interstellar objects like 3 IATLAS can have profound consequences not only for Earth, but for humanity's ambitions across the solar system. If 3I Atlas were to fragment as it approached Earth, the consequences could escalate from a single catastrophic strike to a cascade of destructive events, each capable of leveling cities and wreaking havoc over a wide area. Hypervelocity interstellar objects are subjected to intense tidal forces as they pass near massive bodies like the Sun or planets, as well as extreme thermal stress from solar radiation. If 3I Atlas were already structurally compromised, whether due to internal fractures, compositional inhomogeneity, or previous collisions in interstellar space, the approach could trigger its breakup into multiple large fragments. Each fragment, still traveling at tens of kilometers per second, would carry tremendous kinetic energy, turning what might have been a single catastrophic impact into a series of independent disasters. Instead of concentrating destruction in one location, the energy of the object would be distributed across multiple impact sites, creating widespread devastation across continents. The fragmentation scenario presents unique challenges for both prediction and response. Whereas a single impact allows for a somewhat localized model of damage and evacuation planning, multiple incoming fragments exponentially increase the complexity. Each fragment could be kilometers in size, enough to destroy entire cities upon impact, while smaller fragments could flatten regions, destroy infrastructure, and ignite firestorms over hundreds of kilometers. The distribution of impacts would be largely random, depending on the breakup dynamics, and could strike both land and ocean, creating simultaneous firestorms, tsunamis, and atmospheric perturbations. Emergency management systems would struggle to coordinate responses to multiple simultaneous disasters, overwhelming local and national resources and pushing global disaster response networks to their limits. Secondary and tertiary effects would compound the destruction. Impacts in the oceans could generate tsunamis that hit multiple continents, while land impacts would inject debris and aerosols into the atmosphere, creating localized mini-impact winters in addition to any global climatic effects. The combined dust and smoke from multiple impacts could reduce sunlight far more than a single strike, causing widespread crop failure, disruptions in photosynthesis, and temperature anomalies across the planet. Firestorms ignited by the impacts could merge into massive, uncontrollable conflagrations, releasing carbon and soot into the atmosphere and exacerbating climate disruption. Even regions not directly hit by fragments could suffer from cascading effects, including food scarcity, power outages, and economic collapse. A fragmentation disaster also raises the spectre of unpredictable chain reactions. Smaller fragments that survive atmospheric entry could strike remote areas, triggering wildfires, landslides, or even destabilizing geological features like fault lines or volcanoes. In ocean impacts, multiple tsunamis could interfere with each other, creating irregular wave patterns that extend destruction far beyond typical single-wave models. The multiplicity of impacts means that the timeline of destruction could stretch from the initial impacts into weeks and months afterward. As fires spread, tsunamis continue to propagate, and atmospheric disturbances alter weather patterns globally. From a planetary defense perspective, fragmentation is particularly dangerous because it limits the effectiveness of any potential mitigation strategies. Nuclear deflection or kinetic impact emissions designed to alter the trajectory of a single object would be far less effective if 3I Atlas breaks apart unpredictably in space. Smaller fragments are much harder to detect, track, and deflect, and even partial disintegration could turn a single manageable threat into an unmanageable cluster of high-energy projectiles. The speed of the fragments, inherited from the parent body, would still be extreme, leaving minimal time for Earth-based interventions. Psychologically, a fragmentation event would amplify fear and uncertainty. Populations observing multiple streaks of fire entering the atmosphere could panic, while the sheer scale of simultaneous destruction across multiple regions would challenge the ability of organizations to coordinate effective response. Social cohesion, economic stability, and emergency services could all be severely compromised, compounding the physical effects of the impacts themselves. In essence, fragmentation multiplies the destructive potential of 3IATLAS, transforming a single interstellar strike into a planetary-scale catastrophe with far-reaching ecological, societal, and climatic consequences. If fragments of 3IATLAS were to collide with massive gas giants such as Jupiter or Saturn, the consequences could extend far beyond simple surface impacts, creating a complex cascade of gravitational, atmospheric, and orbital disturbances that ripple through their respective moon systems. Unlike terrestrial planets, Jupiter and Saturn are not solid bodies, but are composed primarily of hydrogen and helium, with dense cores deep within their interiors. When a high-velocity interstellar fragment strikes these planets, the immediate effect would likely be the deposition of enormous amounts of kinetic energy into the upper atmosphere, generating colossal shockwaves, thermal explosions, and massive disturbances in the atmospheric layers. The energy released by even a single kilometer-sized fragment traveling tens of kilometers per second would dwarf any impact previously observed in the solar system, potentially equivalent to multiple nuclear megatons detonating simultaneously. These shockwaves would propagate through the atmosphere, creating extreme turbulence, high-velocity winds, and localized regions of intense heating, altering the chemical balance of the atmosphere and potentially triggering long-lasting storms. The impact of 3 IATL-AS fragments could destabilize the gravitational equilibrium of these giant planets' extensive moon systems. Jupiter alone hosts over 90 known moons, with some like Ganymede, Callisto, Io, and Europa holding substantial mass and complex geological activity. Saturn similarly has more than 80 moons, including Titan and Enceladus, whose orbits and internal dynamics are delicately balanced by tidal interactions. A high-energy impact on the planet's atmosphere, or upper layers, could generate enough mass displacement, shockwaves, or even gravitational perturbation to subtly change the motion of these moons. While the planets themselves are enormously massive and largely immune to trajectory changes from such collisions, the moons orbiting them could experience shifts in eccentricity, inclination, or rotational period. Over time, these changes could lead to cascading orbital instabilities, collisions between smaller moons, or tidal heating effects that destabilize geological and potentially subsurface ocean systems. The atmospheric disturbance caused by a fragment impact could also have a lasting effect on the radiation belts and magnetospheres of Jupiter and Saturn. Both planets possess powerful magnetic fields that trap charged particles, forming intense radiation belts. Displacement of atmospheric gases or injection of high-energy debris could alter the dynamics of these belts, potentially producing spikes in particle flux that impact nearby moons. For example, Europa's subsurface ocean is shielded by its icy crust, but an increase in radiation could alter its surface chemistry, interfere with future exploration missions, and affect the stability of potential habitats. Titan's thick atmosphere could experience heating and turbulence, with storms becoming more extreme, temporarily altering wind patterns and surface pressure in ways that would influence both natural geological processes and human exploration planning. In essence, a fragment impact could indirectly trigger environmental upheavals on moons that are otherwise stable, creating unpredictable hazards for robotic or future crewed missions. Fragment impacts on gas giants could also initiate longer-term orbital and resonance effects within the moon systems. Many moons are locked in orbital resonances that maintain stability over millions of years. A sudden significant perturbation in the planet's mass distribution or an atmospheric explosion on a colossal scale could nudge a moon out of resonance, producing small but cumulative orbital deviations. These deviations might lead to tidal heating in unexpected areas, altering geological activity, or even causing surface cracking, volcanism, or ice movement on moons like Europa, Io, or Enceladus. In extreme cases, fragments impacting the upper atmosphere could inject sufficient momentum to shift the planet's rotation rate imperceptibly but meaningfully over time, subtly altering tidal interactions with multiple moons. This domino effect would be invisible to casual observation, but could destabilize moons over decades or centuries, creating cascading risks for natural satellite systems. Beyond the immediate physics, fragment impacts could pose serious implications for scientific exploration and future colonization ambitions. Many of Jupiter's and Saturn's moons are prime targets for exploration because of their potential subsurface oceans and chemical compositions conducive to astrobiology studies. Europa and Enceladus are particularly intriguing for the search for extraterrestrial life, while Titan offers the possibility of understanding prebiotic chemistry in a dense, nitrogen-rich atmosphere. High-velocity fragment impacts could inject debris and high-energy particles into these environments, contaminating delicate ecosystems or complicating future missions by creating highly irradiated zones and unstable terrain. Planned robotic probes, landers, and orbiters could face severe risk from unanticipated debris streams or altered radiation conditions, forcing mission delays, redesigns, or even cancellations. For crewed exploration efforts projected for the distant future, the unpredictability introduced by such impacts would necessitate additional shielding, real-time monitoring, and contingency planning on a scale far beyond current mission architectures. The psychological and strategic consequences of a planetary chain reaction would be profound. Humanity often perceives space as vast and largely insulated, but the realization that a single interstellar object could indirectly destabilize moons hundreds of millions of kilometers away from Earth challenges that perception. If orbital perturbations or increased radiation levels were observed following a high-velocity fragment impact on Jupiter or Saturn, planetary defense strategies would need to account not just for direct collisions with Earth, but for secondary and tertiary consequences across the solar system. This scenario highlights a sobering truth. The solar system is an interconnected system of delicate gravitational balances, and even seemingly distant events can have cascading effects on exploration, colonization, and scientific understanding. In the most extreme scenarios, cascading effects could produce unexpected chain reactions among moon systems. Collisions or orbital instabilities might eventually generate secondary debris that could leave the gas giant's immediate vicinity, potentially intersecting with asteroid belts, or even paths that bring fragments into the inner solar system. While the probability of such a chain reaction directly threatening Earth is low, the potential for long-term solar system-wide consequences cannot be ignored. These scenarios underscore the fragile balance of planetary and lunar dynamics, where a high-energy interstellar object like 3I Atlas can act as a catalyst, setting in motion events that span millions of kilometers and decades of time. The planetary chain reaction is a stark illustration of cosmic interconnectedness. Even a miss at Earth does not guarantee safety, as the reverberations of a hypervelocity fragment striking a massive gas giant could reshape environments across the solar system in profound and unpredictable ways. In the realm of interstellar speculation, one of the most unnerving possibilities is that 3IATLAS is not a natural object at all, but an artificial construct, an alien probe sent from another star system. Unlike natural interstellar objects, an artificial probe could possess technology far beyond anything humanity has conceived, and its arrival would raise profound questions about intent, design, and potential danger. While no evidence currently indicates that 3I Atlas is artificial, the mere consideration is terrifying. If it were a probe, it could be designed for observation, manipulation, or even a more malevolent purpose. Unlike natural bodies, which operate under the predictable laws of physics and gravity, an intelligent probe could, theoretically, maneuver or emit energy to alter its path, accelerate, or interact with planets and satellites in ways that would be impossible for a conventional rock or comet. The uncertainty surrounding such a possibility amplifies the psychological and practical stakes, turning an already unprecedented interstellar encounter into a scenario reminiscent of science fiction's most chilling concepts. The consequences of an artificial 3IATLAS depend heavily on its size, technology, and purpose. At its most benign, it could be a passive observational device, monitoring the solar system and gathering data much like Earth's telescopes do, but with capabilities beyond human detection. At the other extreme, it could be an active system, capable of deploying energy or matter to alter planetary environments or even target specific sites on Earth. A probe of even modest mass traveling at interstellar velocity would carry enormous kinetic energy, And if equipped with mechanisms to control its trajectory or disperse smaller fragments, it could multiply the potential for destruction. Unlike a natural object, an artificial probe might not rely solely on a ballistic trajectory, introducing an unprecedented layer of unpredictability. Predicting its behavior could be impossible, and humanity's current planetary defense systems, designed for simple deflection or disruption of asteroids, would likely be inadequate against a controlled, intelligent object. The potential for hostility amplifies the threat exponentially. A natural asteroid impact, while catastrophic, is fundamentally blind. It cannot target specific locations or alter its path in response to human intervention. An alien probe, by contrast, could hypothetically respond to our attempts to observe, track, or mitigate it. If it carried mechanisms to accelerate or fragment strategically, it could deliver localized destruction with surgical precision, targeting urban centers or key infrastructure. This worst-case scenario introduces an existential dimension beyond mere physical destruction, because the threat is not just the energy of impact, but the intentional deployment of that energy by an intelligence with unknown objectives. Even a non-destructive probe could carry surveillance or communication technologies that challenge human sovereignty and security, providing extraterrestrial entities with unprecedented access to information about Earth's defenses, communications, and populations. From a scientific perspective, the hypothesis of artificiality would demand intense scrutiny. Every anomaly in trajectory, luminosity, or acceleration could be interpreted as evidence of technology, prompting astronomers and engineers to develop contingency models for interception or monitoring. Unlike ordinary interstellar objects, an artificial 3I ATLAS could be designed to disguise its presence, making it difficult to distinguish from natural asteroids or comets. Its composition, reflective properties, or irregular movements might hint at a technological origin, but interpreting these signals correctly would be an immense challenge, especially given the time constraints imposed by its high-velocity approach. Even minor observational anomalies could indicate either unknown physical phenomena or deliberate manipulation, leaving humanity in a state of profound uncertainty. If 3I Atlas were confirmed to be artificial and potentially hostile, the ramifications for global strategy, science, and society would be staggering. Panic could spread as the population realizes that this is no longer a probabilistic natural threat, but an intelligent actor capable of choosing its targets. Space agencies might abandon conventional exploration missions, focusing resources entirely on defense and observation. The mere potential of an intelligent interstellar object could disrupt international relations, spurring rapid militarization of space and escalating tensions between nations eager to assert control over the planetary defense response. The psychological impact alone would challenge societal cohesion, as humanity confronts the possibility that it is no longer the dominant intelligent presence in its immediate cosmic neighborhood. Even if the object were ultimately non-hostile, the risk remains non-trivial. A technological probe could carry instruments or systems that malfunction in ways catastrophic for Earth, or it might release materials, whether intentional or accidental, that interact dangerously with the atmosphere, magnetic field, or human technology. In effect, the difference between an intelligent but benign probe and a destructive one might hinge on assumptions about alien intentions that we can never verify in advance. The uncertainty of motive, coupled with the sheer kinetic energy of a high-speed interstellar object, elevates the threat scenario far above that of any ordinary asteroid or comet. The prospect of an artificial 3I ATLAS forces humanity to confront uncomfortable truths about our preparedness for extraterrestrial encounters and highlights the limits of our current scientific, technological, and societal frameworks. In conclusion, the possibility that 3IATLAS is an artificial interstellar probe introduces a terrifying layer of complexity and uncertainty to an already unprecedented cosmic event. Unlike natural objects, an intelligent probe could maneuver, fragment, or deploy energy in ways that defy conventional planetary defense strategies. The potential consequences range from catastrophic physical destruction to profound psychological and societal upheaval, depending on the object's technology and intent. Even the hypothesis of artificiality forces humanity to confront vulnerabilities that have largely been theoretical until now, reminding us that interstellar visitors, whether rock or machine, carry risks that are as unpredictable as they are profound. In this worst-case scenario, 3I Atlas is no longer simply a fast-moving rock from another star. It becomes a potential agent of existential threat, capable of challenging human civilization on a scale that eclipses even the most extreme natural impacts. If 3I Atlas were to carry alien microbes or other forms of extraterrestrial life, the implications for Earth would be as profound as they are terrifying. While most interstellar objects are expected to be lifeless, the possibility that a comet-like or asteroid-like body harbors biological material cannot be entirely dismissed. Interstellar travel exposes objects to intense cosmic radiation, high-velocity collisions with dust particles, and extreme cold over millions of years, making the survival of life seem improbable. However, the resilience of extremophiles on Earth, microbes capable of surviving extreme radiation, vacuum, and temperature fluctuations, suggests that life, particularly in dormant or spore-like states, might endure interstellar journeys under protective layers of rock, ice, or organic material. If 3I Atlas carries such microbes and fragments or dust from the object reach Earth, the stage could be set for a form of planetary contamination unlike anything humanity has ever encountered. The potential scenarios for contamination are wide-ranging. Upon atmospheric entry, smaller fragments or dust particles could survive the fiery passage to the surface, embedding alien microbes in terrestrial environments. Even a single gram of material containing resilient microorganisms could theoretically introduce life forms completely alien to Earth's biosphere. Unlike terrestrial pathogens, these microbes would have no evolutionary history with Earth's organisms, and their interactions with ecosystems could be unpredictable and catastrophic. They might outcompete native species, disrupt food chains, or, in the worst case, become pathogenic to humans, animals, or plants. The lack of any prior exposure or immune defenses would leave humans extremely vulnerable, much like historical pandemics, but with an unprecedented scale and novelty that defies conventional medicine or quarantine strategies. The global consequences of such biological contamination would extend far beyond immediate health concerns. Agriculture could be decimated if alien microbes target crops or livestock, leading to food scarcity and famine on a massive scale. Water systems could become contaminated, making drinking water unsafe and complicating sanitation efforts. Entire ecosystems could face collapse if alien organisms propagate rapidly, upsetting the delicate balance between species that has developed over billions of years. The introduction of a completely foreign biosphere could also accelerate the extinction of native species, resulting in a permanent loss of biodiversity. Unlike a meteor impact that is localized, biological contamination has the potential to spread globally, affecting continents and oceans alike, and persisting for decades or centuries if containment proves impossible. From a scientific standpoint, detecting and mitigating such a threat would be extraordinarily difficult. Current planetary protection protocols are designed to prevent contamination from human spacecraft, but they are not optimized for naturally arriving interstellar microbes. Identifying alien life forms requires sophisticated laboratory facilities and rigorous containment measures. Yet initial exposure on Earth could be rapid, and initial outbreaks could occur before any detection is possible. Attempts to neutralize the microbes might fail if they possess biochemical pathways or resistances entirely unknown to terrestrial science. Even measures like quarantining impacted areas would be insufficient if microbial dispersal occurs through wind, water, or animal vectors, as these pathways could carry alien organisms far from the initial impact site. In a worst-case scenario, alien microbes could trigger a global pandemic unlike any in history, with mortality rates, contagion patterns, and ecological disruption beyond human experience. The combined effect of infection, environmental collapse, and societal panic could mirror or exceed the consequences of a major asteroid impact, except that the danger would not be localized and instantaneous, but diffuse, persistent, and globally distributed. Contingency planning would require not only medical and ecological interventions, but also unprecedented coordination in policy, international relations, and scientific research to contain the spread of a truly alien pathogen. Even if the microbes prove non-pathogenic to humans, they could still alter Earth's ecosystems in unpredictable ways, changing the evolutionary trajectory of species and introducing new biochemical cycles. The introduction of extraterrestrial genetic material could have long-term, transformative effects on terrestrial life, creating organisms with novel traits or entirely new ecological interactions. Humanity would need to adapt to a planet in which the foundational biological assumptions are no longer guaranteed, confronting the reality that interstellar objects are not just inert hazards but potential vectors for life that operates by rules entirely unknown to us. If 3I Atlas were to impact Earth, one of the most devastating consequences could be a nuclear winter-style scenario, in which the enormous quantities of dust, ash, and vaporized rock ejected into the atmosphere block sunlight for months or even years. The concept of nuclear winter was first studied in the context of large-scale nuclear warfare, but its mechanics apply equally to massive asteroid or comet impacts. Upon collision, the energy released would vaporize surface material at the impact site, sending it soaring into the stratosphere. Unlike ordinary weather events, this material would linger at high altitudes, preventing sunlight from reaching the surface. Global temperatures would plummet, creating a prolonged period of darkness and extreme cold that could destabilize agricultural systems, ecosystems, and human civilization alike. Crops would fail almost universally as photosynthesis is reduced or halted, leading to widespread famine. Even regions far from the impact site could experience temperatures several degrees below seasonal norms, disrupting normal weather patterns, intensifying storms, and triggering unusual climate phenomena. The scale of such a nuclear winter would depend on the size and composition of 3 IATLAS, but even a modest interstellar object traveling at tens of kilometers per second carries energy far exceeding the largest nuclear detonations in human history. A kilometer-sized fragment impacting the Earth could inject tens of billions of tons of particulate matter into the atmosphere, creating a dense, sun-blocking haze that persists for years. Volcanic analogues suggest that once dust and aerosols reach the stratosphere, they are resistant to precipitation and can circulate globally, spreading the cooling effect across continents. Crop failures would not be isolated but synchronized globally, leading to simultaneous food shortages in multiple regions. The interconnected nature of modern supply chains would amplify this effect, as the collapse of one major agricultural region could create cascading shortages worldwide. Even societies with abundant resources could struggle to maintain stability under conditions of chronic scarcity and extreme climate stress. Beyond immediate human concerns, the ecological consequences would be equally severe. Plankton, the base of oceanic food chains, depends on sunlight for photosynthesis. Reduced sunlight would starve these organisms, cascading upward through marine ecosystems and causing mass die-offs of fish, mammals, and other oceanic species. Terrestrial ecosystems would also be affected. Forests and grasslands could fail to grow, altering animal populations and disrupting natural cycles. The loss of vegetation would reduce carbon sequestration, compounding climate disruption. Animal migrations could be disrupted, and many species would face heightened risk of extinction as survival strategies fail under prolonged darkness and cold. Ecosystems that have evolved over millennia to handle seasonal variation are ill-equipped to adapt rapidly to a global-scale nuclear winter, making the threat to biodiversity extreme. The psychological toll of a prolonged nuclear winter would also be immense. Humanity would face near-constant darkness in regions far from the equator, creating widespread mental health crises, including depression, anxiety, and despair. The perception of safety and predictability would be shattered, as even distant populations experience the tangible effects of a single catastrophic event. Communities might fracture, with trust eroding as resource scarcity and survival instincts dominate social interactions. Education, healthcare, and cultural continuity could all be disrupted, threatening the long-term cohesion and knowledge transfer essential for recovery and rebuilding. The human experience under prolonged nuclear winter would be one of struggle not just for survival, but for the preservation of societal structure and cultural identity. Compounding the human and ecological crises, a nuclear winter caused by 3 IATLAS could trigger feedback loops that exacerbate its effects. Reduced sunlight could alter precipitation patterns, potentially triggering droughts in some regions and flooding in others. Atmospheric cooling could destabilize polar ice caps, altering ocean currents and creating further climate instability. The cumulative effect of these changes would make recovery extremely slow, potentially spanning decades or centuries. Humanity might survive, but the social, technological, and ecological setbacks could push civilization back by centuries, resetting progress in agriculture, industry, and scientific knowledge. In summary, the nuclear winter scenario following a 3 IATLAS impact represents one of the most catastrophic potential consequences of interstellar collision. Beyond the initial firestorms and tsunamis, the prolonged blockage of sunlight would create cascading effects across ecosystems, human society, and the global climate. Food scarcity, mass migrations, societal collapse, and ecological disruptions would all unfold simultaneously, producing a multi-layered catastrophe that could challenge the resilience of human civilization on a planetary scale. Even regions not directly struck by fragments or debris would feel the chilling, sunless reality of a world plunged into years of darkness and extreme cold, demonstrating that the true power of an interstellar impact extends far beyond its immediate physical devastation. Beyond the immediate kinetic and climatic threats posed by an interstellar object like 3I Atlas, some of the most unsettling worst-case scenarios involve the speculative disruption of Earth's magnetosphere. The magnetosphere is the invisible magnetic shield that surrounds our planet, protecting it from the relentless bombardment of solar wind, cosmic radiation, and high-energy particles. It deflects charged particles that would otherwise strip away the atmosphere, damage electronics, and expose living organisms to lethal doses of radiation. If 3I Atlas were not merely a rock, but carried unusual electromagnetic properties, or if its impact, or near miss, interacted with Earth's magnetic field in unexpected ways, the consequences could be profound, extending far beyond localized physical damage to compromise the planet's long-term habitability. One possible mechanism for magnetospheric disruption is the generation of strong electrical currents during the interaction of highly charged fragments with the Earth's magnetic field. Interstellar objects moving at tens of kilometers per second carry not just kinetic energy, but also electromagnetic potential, especially if composed of conductive materials, magnetized metal, or exotic matter. When such a body approaches the Earth, its rapid motion through the magnetic field could induce localized geomagnetic storms far beyond those naturally caused by solar activity. These storms could temporarily distort the shape and orientation of the magnetosphere, allowing energetic particles to penetrate regions usually protected by the magnetic shield. Satellites and spacecraft would be at immediate risk of damage from the sudden influx of radiation and charged particles, potentially destroying GPS, communication, and weather monitoring systems. Power grids on the ground could also be affected, as geomagnetic-induced currents propagate along transmission lines, causing blackouts and electrical fires in highly developed urban areas. In an even more extreme scenario, fragments or dust from 3I Atlas could generate localized but intense electromagnetic pulses, EMPs, upon interaction with the upper atmosphere or the magnetosphere itself. Unlike nuclear-generated EMPs, which have been studied extensively for defense planning, an interstellar object could produce pulses of unpredictable magnitude, duration, and spatial coverage. Such pulses could fry electronics on a continental scale, incapacitating satellites, aircraft systems, electrical grids, and even smaller electronic devices essential for daily life. The economic, technological, and logistical repercussions would be staggering, effectively immobilizing modern societies in the midst of a simultaneous natural catastrophe. Unlike a direct impact or tsunamis, magnetosphere disruption could affect regions far from the site of any physical strike, creating a global-scale technological emergency. The sudden loss of digital infrastructure could amplify the humanitarian crisis following other impact-related disasters such as fires, tsunamis, or climate disruption. Magnetospheric instability could also exacerbate other environmental effects. A weakened magnetic shield allows higher levels of cosmic radiation to reach the Earth's surface and upper atmosphere. Increased radiation exposure could damage the ozone layer, amplify ultraviolet radiation reaching the ground, and create harmful conditions for both terrestrial and marine life. Aircraft crews, space missions, and populations at high altitudes would face elevated health risks, while disruptions to atmospheric chemistry could alter weather patterns and long-term climate dynamics. Prolonged disturbances might even accelerate atmospheric erosion in subtle ways, particularly if combined with other catastrophic events, like dust from a nuclear winter scenario, compounding the existential threat posed by the interstellar encounter. The societal consequences of magnetosphere disruption, though largely indirect, could rival or exceed those of direct impact events. Modern civilization is deeply dependent on electronics, satellites, and communication networks, which are vulnerable to electromagnetic interference. Navigation, financial systems, global communication, and even food distribution rely heavily on technologies susceptible to EMP-like effects. Widespread failure of these systems could trigger social unrest, mass panic, and economic collapse. Emergency services, already stressed by environmental disasters caused by impact or climate anomalies, would face compounded challenges, unable to coordinate or respond effectively without functional communication networks. For populations in urban areas, the sudden cessation of electricity and electronic infrastructure could have immediate life-threatening consequences, from the failure of hospitals and water systems to the inability to maintain food refrigeration or heating in extreme climates. While this scenario is highly speculative, the physics of magnetospheric interaction with high-energy interstellar objects is not entirely implausible. The unpredictability lies in the combination of factors: the object's velocity, composition, size, and potential magnetic or conductive properties. Even minor deviations from expected behavior could produce amplified geomagnetic disturbances, illustrating how a non-impacting interstellar visitor could still destabilize Earth on a global scale. Unlike other worst-case scenarios where destruction is localized to the impact zone, magnetosphere disruption demonstrates the vulnerability of technologically dependent civilizations to phenomena that are invisible, silent, and nearly instantaneous, yet capable of affecting every corner of the globe. In essence, the speculative disruption of the magnetosphere elevates the threat of 3IATLAS from a purely physical hazard to a technologically existential one. Even without direct collision, its passage could trigger electromagnetic and radiation effects capable of incapacitating modern infrastructure, endangering human health and exacerbating ongoing climate and environmental crises. It highlights the delicate balance between Earth's protective natural systems and human technological reliance, revealing how an interstellar visitor could exploit this intersection in ways that are difficult to predict, mitigate, or defend against. In combination with other potential consequences, fragmentation, climate disruption, or biological contamination, magnetosphere disruption adds a silent but potent layer of danger, transforming 3IATLAS from a fast-moving cosmic rock into a multi-dimensional threat to the stability of civilization. Taking the speculation to its most extreme, one of the most unsettling possibilities is that 3IATLAS is not a conventional object at all. Rather than a rock, comet, or even an artificial probe, it could be something entirely stranger, an entity or phenomenon composed of exotic matter, an interdimensional remnant, or a manifestation of unknown physics that challenges the very foundations of our understanding. Exotic matter, theorized in physics but never directly observed, could have properties that defy conventional interactions: negative mass, gravitational repulsion, or the ability to distort spacetime in unusual ways. If 3I Atlas were composed of such matter, its approach toward the inner solar system could produce effects far beyond ordinary impact predictions. Gravity anomalies, unexpected accelerations, or disruptions of planetary orbits could occur simply through its presence, independent of collision. In this scenario, the danger is not limited to kinetic energy or climate effects. The mere existence of the object in proximity to Earth could trigger events that are currently beyond our capacity to predict or model. The possibility that 3I Atlas represents a physics-defying phenomenon opens the door to scenarios that border on science fiction, yet are considered in serious theoretical discussions. If it is a concentration of exotic energy or matter, its interaction with normal matter could be highly destructive. For example, the object could induce localized distortions in space-time, potentially altering the passage of time, generating intense tidal forces, or creating localized gravitational anomalies. These effects might not even require direct contact with Earth. The object could destabilize satellites, influence the orbits of small bodies in the solar system, or generate catastrophic effects in regions of high density or tectonic instability. Unlike a conventional asteroid or comet, such an entity could operate under physical principles that do not scale linearly with size or distance, meaning even a small fragment or a non-colliding passage could trigger disproportionately large consequences. If 3I Atlas were capable of weaponizing unknown physics, the implications are nearly incomprehensible. An exotic object could, in principle, manipulate electromagnetic fields, gravitational waves, or space-time itself in ways that directly threaten planetary stability. Hypothetical effects might include the instantaneous release of vast amounts of energy, creating explosions or radiation bursts without an apparent source, the localized collapse of geological structures, or the destabilization of orbital systems in ways that propagate chaos through the solar system. In such a scenario, the distinction between impact, near miss, or distant passage becomes largely irrelevant, because the interaction of exotic matter with the environment could produce catastrophic outcomes regardless of classical trajectories. Traditional defense strategies, including deflection or evacuation, would likely be ineffective as they assume predictable behavior based on Newtonian mechanics, a framework that may not apply to such a phenomenon. The psychological and societal implications of encountering a non-ordinary interstellar visitor are as profound as the physical dangers. Humanity relies on a stable understanding of natural law to manage risks. An object whose behavior violates or circumvents known physics would confront societies with an existential uncertainty that cannot be mitigated through conventional planning. Panic and societal stress could escalate rapidly if observational anomalies suggest the object is not obeying standard physical laws. Scientific communities would scramble to understand, model, and predict behavior, yet any predictive success might be limited, leaving decision-makers to respond to a fundamentally unpredictable threat. The disruption to human civilization might be as much psychological and technological as it is physical, emphasizing the profound vulnerability inherent in encountering phenomena that challenge our understanding of reality. Even on a speculative level, considering 3I Atlas as exotic or physics-defying forces us to confront the limitations of humanity's current technological and scientific readiness. Planetary defense strategies, predicated on intercepting or deflecting conventional asteroids, are insufficient against objects that may not obey known laws or that interact with matter and energy in unknown ways. Global preparedness plans would be rendered ineffective, leaving humanity to react to events as they unfold, rather than proactively mitigating them. In this sense, 3I Atlas embodies the ultimate cosmic uncertainty. It is a variable that cannot be measured or controlled with existing knowledge, a reminder that the universe may harbor forces and entities far beyond the scope of current human comprehension. Even if 3I Atlas were to miss Earth entirely, its passage through the inner solar system could still trigger catastrophic consequences for humanity by disrupting the fragile network of satellites, space stations, and orbital infrastructure that modern civilization relies upon. Low Earth orbit is densely populated with satellites that enable global communications, navigation, weather forecasting, and military operations. A high-speed fragment or a cloud of debris from 3I Atlas could collide with even a single satellite, generating a chain reaction known as the Kessler syndrome, where one collision produces debris that strikes other satellites, exponentially multiplying hazards in orbit. In a worst-case scenario, this cascade could compromise critical communication systems, GPS navigation, early warning networks for natural and man-made disasters, and the operation of military satellites, effectively paralyzing modern societies reliant on these systems. The International Space Station, already vulnerable due to its low orbital altitude, could face immediate threats from both direct impacts and high-velocity microdebris. Even particles smaller than a centimeter can puncture or damage modules, solar panels, or life support systems at orbital velocities exceeding 7 kilometers per second. A fragment from 3 IATLAS, or secondary debris generated by collisions with existing satellites, could compromise the station's integrity, forcing emergency evacuations, or, in the worst case, rendering the ISS inoperable. Loss of this platform would not only end scientific research, but would also significantly impair Earth's capacity to monitor near-space hazards, leaving humanity blind to additional incoming threats. Beyond physical damage, disruption of satellites would have cascading effects on terrestrial systems. Global banking, transportation, air traffic control, logistics, and military command systems all depend on satellite networks for real-time data. A massive outage would hinder disaster response, reduce situational awareness during environmental crises, and undermine national security. Without GPS and accurate communication, aviation systems would struggle to operate, maritime navigation could fail, and supply chains could collapse, leading to shortages of essential goods. The disruption would be global, indiscriminate, and immediate, striking at the heart of technological civilization, even without direct physical impacts on the planet's surface. The economic and strategic consequences are similarly dire. The destruction or impairment of commercial satellites could cost tens or even hundreds of billions of dollars, while insurance systems may struggle to compensate for the unprecedented scale of losses. Military satellites, including reconnaissance, communication, and early warning systems, would be vulnerable to both accidental debris collisions and deliberate miscalculations during a crisis. The vulnerability of space infrastructure would expose the fragility of global defense networks, leaving nations blind and uncoordinated in their response to subsequent threats, whether from natural interstellar objects, solar events. Even minor orbital debris could amplify risk for decades as fragments continue to circulate in orbit, posing long-term hazards to new launches and complicating the reconstruction of critical satellite constellations. The chain reaction is not confined to near-Earth orbit. If fragments of 3 IATLAS, or debris from its interaction with satellites, reach higher altitudes, they could threaten geostationary satellites critical for communications and television broadcasts, or even scientific satellites monitoring climate, oceans, and planetary health. Disruption in these areas would compromise climate monitoring, early detection of extreme weather, and global scientific research, producing effects that ripple from the technological to the environmental. Even if humanity survives the initial orbital chaos, rebuilding these essential systems could take years, leaving civilization vulnerable to compounded natural and technological disasters. Furthermore, space exploration efforts would face devastating setbacks. Missions to the Moon, Mars, and beyond could be delayed or cancelled due to an unsafe orbital environment, threatening decades of investment and scientific progress. Robotic missions could fail due to debris impacts, communication blackouts, or power losses, while crewed missions would face unacceptable risks. The progress of human expansion into space, seen by some as a hedge against planetary catastrophes, could be brought to a standstill, leaving Earth as the sole refuge in a suddenly more hostile solar system. In this sense, 3I Atlas could indirectly threaten not only terrestrial civilization, but also humanity's long-term survival prospects in space. In conclusion, even without striking Earth, 3IATLAS could unleash a cascade of failures across orbital infrastructure, satellites, and space-based systems that underpin modern civilization. From communication and navigation to defense and space exploration, the interconnected networks humans depend upon are vulnerable to a single high-velocity object or its secondary debris. The result could be a global technological paralysis, complicating response to any additional disasters while delaying scientific and exploratory progress for decades. This scenario highlights a unique dimension of cosmic vulnerability. The threat is not only physical, but structural, exploiting humanity's reliance on fragile orbital systems to produce disruption, fear, and long-term instability. Humanity's current defenses against interstellar objects, like 3 IATLAS, are remarkably limited, highlighting a profound vulnerability that becomes especially apparent when considering worst-case scenarios. While space agencies have been developing asteroid detection and deflection technologies for decades, these systems are largely designed to deal with objects that are slow-moving relative to Earth and have been observed for months or even years before any potential collision. Interstellar visitors, by contrast, move at incredible velocities, tens of kilometers per second, and arrive from unknown directions, often with trajectories that are extremely difficult to predict in advance. Unlike ʻOumuamua or Borisov, which pass through the solar system without posing a direct threat, 3 IATLAS's approach was only detected on July 1, 2025, leaving humanity with an extremely short window to respond. The rapid detection-to-threat timeline severely limits the practical options for mitigation, making the probability of an effective defense alarmingly low. Current planetary defense technologies primarily revolve around kinetic impactors, gravity tractors, or, in more theoretical scenarios, nuclear detonations to alter an asteroid's trajectory. Kinetic impactors require precise targeting, significant lead time, and knowledge of the object's composition to work effectively. A fast-moving interstellar object, like 3I Atlas, reduces the time available for such interventions to mere months or weeks. The object's composition, whether solid rock, icy comet, or loosely bound rubble, further complicates matters. A nuclear explosion might fragment a loosely bound object, creating multiple high-speed city-killer fragments, rather than neutralizing the threat. Even if deflection is theoretically possible, the high relative velocity of 3 IATLAS limits the effectiveness of conventional kinetic or explosive methods, as any course alteration must occur extremely early in the object's approach, time that is simply unavailable with late detection. Detection capabilities themselves remain a significant bottleneck. Most current telescopes and survey systems are optimized for near-Earth asteroids and slower-moving solar system objects. Interstellar bodies, approaching from unknown angles and often with low reflectivity, can easily evade early detection. The late discovery of 3 IATLAS exemplifies this vulnerability. Had its trajectory been slightly more aligned with Earth, humanity might have had only weeks or even days to respond. This brief reaction window would render even the most advanced kinetic interceptors ineffective, forcing reliance on last resort or improvised measures with no guarantee of success. Additionally, coordination between nations and agencies, while improving in recent years, is far from streamlined enough to execute a rapid planetary-scale mitigation campaign on such short notice. The logistical challenges of mounting a defense are equally daunting. Deploying interceptors or mitigation devices against an object moving at interstellar speeds would require unprecedented launch capabilities, extremely precise calculations, and near instantaneous mobilization of resources. Even minor miscalculations in trajectory or timing could result in total failure, while errors in fragmentation or deflection could exacerbate the situation, turning a single object into multiple hazards. Humanity's current stockpiles of nuclear explosives, designed for terrestrial or near-space deployment, are not optimized for this type of high-velocity, high-uncertainty scenario. Moreover, international treaties and protocols governing the use of such weapons in space complicate rapid deployment, introducing potential delays at a moment when speed is critical. Beyond technological and logistical limitations, psychological and societal factors further restrict humanity's ability to mount an effective defense. The realization that a massive interstellar object could strike Earth with little warning could induce panic, complicating orderly evacuation or mitigation efforts. Coordinating a global response to a short-notice, unprecedented threat would require unprecedented levels of trust, cooperation, and communication among nations, qualities that have historically been fragile during crises. Even with perfect technology, human factors such as indecision, bureaucratic delays, and miscommunication could drastically reduce the effectiveness of defensive measures, leaving populations exposed to catastrophic outcomes. The stark truth is that humanity is largely powerless against 3 IATLAS in its current state of preparedness. Unlike threats that are familiar or have predictable dynamics, interstellar objects operate outside the parameters for which planetary defense systems were designed. While detection and mitigation technologies continue to improve incrementally, the combination of high velocity, late detection, and potential unconventional composition makes an effective response highly uncertain. Even theoretical solutions, such as gravitational tractors or coordinated nuclear deflection, remain untested on the scale and timing required for interstellar threats. The reality is that, without significant advances in early detection, rapid response capabilities, and international coordination, a high-speed interstellar object approaching Earth represents a near-impossible challenge to our current planetary defense infrastructure. Despite the terrifying scenarios described so far, it is important to contextualize the arrival of an object like 3 IATLAS within the vast timescales and probabilities of cosmic events. Interstellar visitors are extraordinarily rare. Only 3 have been detected entering the solar system: ʻOumuamua in 2017, Borisov in 2019, and 3I Atlas in 2025. The vast majority of material passing through interstellar space never intersects with our tiny planet. Statistically, the odds of a high-velocity object striking Earth in any given year are minuscule, meaning humanity is extremely unlikely to face such a catastrophe on an annual basis. Yet rarity does not eliminate risk entirely, and the potential consequences of a direct collision or near miss are so extreme that even low-probability events demand careful consideration. This juxtaposition, rare occurrence but extreme consequence, is what makes interstellar objects such as 3I Atlas a part of the cosmic lottery. The universe occasionally deals a hand so devastating that it could reset civilization entirely. The concept of a cosmic lottery illustrates both the unpredictability and the high stakes of interstellar impacts. Unlike predictable terrestrial hazards such as hurricanes, earthquakes, or volcanic eruptions, which occur in familiar patterns and locations, interstellar objects appear suddenly, moving at extraordinary velocities from unpredictable directions. Humanity cannot rely on historical precedent or regional knowledge to anticipate such events. Every interstellar arrival is unprecedented and unique. The sheer scale of the solar system relative to the Earth, combined with the extreme speed and small size of many interstellar objects, makes detection difficult and warning time short. As a result, Earth exists under a latent risk of catastrophic disruption that is extraordinarily low in probability, but nearly infinite in consequence. Even a single collision with an object like 3 IATLAS has the potential to reset civilization in profound ways. Large impacts can trigger firestorms, tsunamis, climate collapse, nuclear winter, and widespread infrastructure disruption, leading to mass mortality, societal upheaval, and collapse of technological networks. Historically, Earth has experienced similar events. The Chicxulub impact 66 million years ago wiped out the dinosaurs and fundamentally reshaped terrestrial ecosystems. A comparable event today would not only devastate human populations, but could also erase cultural knowledge, technological progress, and economic stability, setting humanity back potentially by centuries. Unlike smaller, localized natural disasters, an interstellar impact has the power to disrupt planetary systems on a global scale, affecting every continent simultaneously and leaving no region untouched. In essence, while the odds of such a catastrophe are low, the stakes are unmatched. Humanity's very survival and the continuity of civilization hang in the balance. The rare but potentially catastrophic nature of interstellar objects also underscores a critical paradox of preparedness. Because these events are so unlikely, societies tend to underinvest in detection, research, and mitigation. This creates a situation in which humanity is vastly unprepared for a catastrophe that could, if it occurs, have existential consequences. Early warning systems, deflection technologies, and emergency response plans are all geared toward more common terrestrial hazards, leaving interstellar objects like 3I Atlas largely unaccounted for. The universe's randomness in sending high-velocity objects toward Earth means that even a single oversight in detection or response could result in an irreversible disaster. This is the essence of the cosmic lottery: low-frequency, high-impact events that could strike at any moment, bypassing all conventional human safeguards and leaving civilization at the mercy of chance. Furthermore, the cosmic lottery concept reminds us that humanity's perceived control over its environment is fundamentally limited on a cosmic scale. While humans have learned to mitigate earthquakes, hurricanes, and other planetary hazards, interstellar objects exist entirely outside the parameters of terrestrial experience. Their arrival is not seasonal or geographically predictable. It is determined by dynamics that span light years and eons. In this sense, Earth's position in the universe is precarious, reliant on both cosmic luck and technological foresight. Even the most sophisticated detection systems can fail if an object arrives unexpectedly or exhibits unconventional behavior, such as unusual trajectories, fragmenting unexpectedly, or carrying exotic properties. The universe's impartiality is absolute. Probability does not confer immunity, and rare events, when they occur, can deliver consequences that dwarf all human preparedness. As 3I Atlas hurtles through our solar system, it serves as a stark reminder of the dual nature of interstellar visitors. They are both emissaries of knowledge and harbingers of unimaginable risk. These rare objects, traveling across light years of void, carry with them the chemical and physical signatures of other star systems, offering scientists a fleeting opportunity to glimpse the diversity of planetary formation, stellar evolution, and perhaps even the building blocks of life beyond Earth. Each interstellar arrival pushes the boundaries of our understanding, challenging assumptions, inspiring curiosity, and igniting the human drive to explore. From a purely scientific perspective, 3I Atlas and its predecessors, like ʻOumuamua and Borisov, are cosmic messengers, delivering insights that no terrestrial experiment could ever replicate, and reminding us that the universe operates on scales, both temporal and spatial, far beyond human experience. Yet this wonder is inseparably intertwined with peril. The very characteristics that make 3I Atlas fascinating, its speed, its unknown composition, its unpredictable trajectory, also make it a potential existential threat. From catastrophic impact scenarios, nuclear winter, and planetary chain reactions to more speculative dangers like magnetosphere disruption or exotic physics phenomena, the object embodies the immense uncertainty and fragility of human civilization, when confronted with forces beyond our control. It exposes the limitations of our technological preparedness, the vulnerability of our orbital infrastructure, and the societal fragility that could be exploited by a high-energy event originating from the cosmos. The awe-inspiring scale of interstellar travel and the scientific promise it holds is inseparable from the sobering reality that even a single miscalculation, fragment, or unanticipated property could trigger devastation on a planetary scale. This thin line between wonder and doom defines humanity's relationship with the cosmos. Every observation, every new discovery is a dance between curiosity and caution, a reminder that the pursuit of knowledge often comes with inherent risks. While we have the capacity to marvel at the chemical fingerprints, trajectory anomalies, and interstellar origins of 3 IATLAS, we must also acknowledge that our understanding is incomplete and our defenses are limited. The universe is generous with opportunities for discovery, but indifferent to the consequences of our exposure to phenomena that operate on scales and under rules that may be wholly alien to our experience. In contemplating objects like 3 IATLAS, humanity is faced with the exhilarating possibility of insight and the chilling potential for catastrophe, two sides of the same cosmic coin. The passage of such an interstellar object is also a reminder of our place within the broader universe. For all our technological sophistication and planetary engineering, we remain small, fragile, and highly susceptible to events that unfold on cosmic timescales. Yet it is precisely this fragility that sharpens the significance of discovery. Each encounter challenges us to expand our knowledge, to improve our preparedness, and to appreciate the delicate balance that sustains life on Earth. The presence of 3I Atlas evokes both humility and urgency, demonstrating that while the universe offers unparalleled opportunities for observation and understanding, it also possesses the capacity to reshape civilizations in an instant. Awe and anxiety coexist, entwined by the simple fact that the cosmos is vast, indifferent, and occasionally intrusive. Ultimately, interstellar visitors like 3 IATLAS are emblematic of the paradox that defines humanity's exploration of space. The same object that extends our knowledge can also threaten our survival. Our fascination with the cosmos is inseparable from the risks inherent in encountering it, and every scientific triumph carries with it an implicit reminder of our vulnerability. The thin line between wonder and doom is crossed not through recklessness, but by the sheer reality of the universe's scale and unpredictability. In watching 3I Atlas streak across the solar system, humanity witnesses a moment where curiosity meets caution, knowledge meets uncertainty, and the thrill of discovery is inseparable from the contemplation of existential risk. In the end, the story of 3 IATLAS is not merely about an interstellar visitor passing through our solar system. It is about the delicate balance between insight and imperilment, between fascination and fear, that defines our relationship with the cosmos. It challenges us to prepare, to observe, and to marvel, all while acknowledging that some forces in the universe are far greater than our ability to control them. Humanity's journey among the stars will always navigate this thin line, and every rare, high-velocity visitor, like 3 IATLAS, is a reminder that exploration comes with both extraordinary knowledge and the humbling awareness of our own cosmic vulnerability. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.